In this video, we're going to be talking about Unit 3, Objective 3.4, Ideal Gas Law. Our topic is to explain the relationship between the macroscopic properties of a sample of gas or mixture of gases using the ideal gas law, and our skill is mathematical routines. So the key point is that the macroscopic properties of ideal gases are related through the ideal gas law. This gas law is PV equals nRT. It's also sometimes referred to as PIV-NERT. P is pressure in ATM, V is volume in liters, N is the amount of gas in moles, R is our gas constant, and this is a constant, so this is a number that never changes, and it's 0.08206 liters ATM per mole Kelvin. And T is temperature in Kelvin. This is a reference sheet from AP, the AP reference sheet. And notice we have our ideal gas law, PV equals nRT. This equation right here is our moles equals the grams, the mass, divided by our molar mass. Another way of thinking about this is that our molar mass is in units grams per mole. So it's equal to mass per moles, grams per mole. And then we have this equation helps us convert from degrees Celsius into Kelvin. So notice if it was 0 degrees Celsius, it would be 273 Kelvin. And our temperature always has to be in units of Kelvin. So make sure to use that equation. And this is just our density equation. Density equals mass over volume. Here you can see what all of these variables mean. Our gas constant, again, is always this number with these units. So that's why we need to have these 4 units as P, V, N, and T. And then just to convert between pressure, 1 ATM is equal to 760 mmHg, millimeters of mercury, or 760 torr. Whenever you hear STP, that means standard temperature and pressure, and that means that we're at 0 degrees Celsius, or 273.15 Kelvin, and 1 ATM. And then if we have an ideal gas at standard temperature and pressure, 1 mole of that gas is 22.4 liters. And we're going to examine this equation right here and prove that it's correct by using the ideal gas law. So this is what it's saying. It's saying that at standard temperature and pressure, 22.4 liters is equal to 1 mole. So we're going to use the ideal gas law. And we know that at standard temperature and pressure, our pressure is 1 ATM. We are looking for our volume. We're going to try and prove that our volume is equal to this. So we're going to have 1 mole. Our gas constant never changes, that's our constant, and our temperature at standard temperature and pressure is 273. And I know the reference sheet says 273.15, and you can also use that number, and that will get you a more exact, it'll have a few more significant figures that are exact. So we're going to be solving for volume. So in order to do that, we're going to rearrange this equation and divide by pressure to get volume alone. And now we're just going to plug in all these numbers. So we have 1 mole for our N, our gas constant R, our temperature at standard temperature, so that's 273, and our pressure at standard pressure. So notice that mole cancels out with mole, liter does not cancel. There's nothing there. ATM, we're dividing by an ATM, so that cancels. We have Kelvin to the -1, so that's like divided in the denominator, and we have Kelvin in the numerator. So we're left with units of liters, which is good because we're looking for volume. So when you plug all this into your calculator, you get 22.4 liters. So this is indeed correct. So now we're going to try a practice problem. The pressure in ATM exerted by 1.85 moles of an ideal gas placed in a 3-liter container at 35 degrees Celsius is given by which of the following expressions? Okay, so as you can see, we are looking for pressure. So that's what we're looking for. And we're given a few pieces of information. We're given that our moles is 1.85. We're given that our volume is 3 liters. we're given that our temperature is 35 degrees Celsius, but remember we have to convert that into Kelvin. So we do 35 plus 273 to get our 308 Kelvin. And then we know this equation, PV equals nRT. We are solving for pressure, so we're going to divide both sides by volume. And so then we have N times R times T divided by volume. So just by glancing at these, you can see that B, C, and E are incorrect because we just want volume in the denominator. So 3 belongs in the denominator, and the difference between A and D is this gas constant. And our gas constant R is 0.0821. In D, they tried to trick you by using the other R, but remember, our units need to work. So we need to use the R that has liters, ATM, mole, and Kelvin, not joules. So the answer is A. A 2-liter container will hold about 4 grams of which of the following gases at 0 degrees Celsius and 1 atm? Okay, so we're given a few pieces of information. Our volume is 2 liters, and our mass is 4 grams. And this is at standard temperature and pressure. So remember, at standard temperature and pressure, 1 mole is equal to 22.4 liters. We also know that molar mass is equal to grams per mole. Now, all of these answers have different molar masses. So if we know the molar mass of our sample, then we can figure out which gas we would have. So our molar mass is in units of grams per mole. Well, we're given grams right here. And to get our moles, we know that we have 2 liters and that 1 mole is equal to 22.4 liters. So we can have our mass on top, 4 grams, and we know that 2 liters, 1 mole is 22.4 liters. So if we do 2 divided by 22.4, we should get how many moles we have. So another way of writing this, because we have a fraction in the denominator, we can just bring that up and flip it. So it's really 4 grams times 22.4 liters divided by 2 liters times 1 mole. And notice our liters cancel out, and we're left with grams per mole, which is our unit of molar mass. And so 4 times 22.4 is, 4 divided by 2 times 22.4 is 44.8 grams per mole. And so that is the molar mass of carbon dioxide. Because carbon has a mass of about 12, O2, 16 times 2 is 32, so that's about 44. You can eliminate, S has a mass of 32, so this is like 32 plus 32, so that's too big. N has a mass of 14, so this would be 28, 14 times 2. C4H8, so that's like 12 times 4 plus 8, so that's also too big. And then we would have 14 plus 3. So carbon dioxide is the correct answer. This question refers to 3 gases in identical rigid containers under the conditions given in the table below. So here you have our containers, our gas, our formula for those gases, the molar mass, the temperature, and the pressure. The density of the gas in grams per liter is greatest in container A, greatest in container B, greatest in container C, or the same in all 3 containers. So we're not told the volume, but we're told that we have identical rigid containers. So we can assume that the volume is the same in each. So I'm just going to assume 1 liter container. You could assume any volume, but 1 is just an easy, mathematically, it's easy to work with. We are given molar mass, so we're really looking for grams per liter. So now I have the liters. I'm assuming one liter. And so now I need to figure out the grams I have of each gas. So I know that molar mass is equal to grams per mole. So I'm going to be comparing this, my molar masses. And so if I were to solve for my grams, then I would have molar mass times moles. So I have my molar mass, but I don't have my moles. That's what I need to figure out. If I take my ideal gas law, I can solve for moles by dividing by RT on both sides. So notice, my temperature is exactly the same in all of them. So that's not going to affect my amount, the difference in my amount of moles. The gas constant is also the same. It's a constant. So that won't affect it. I already said that I have a 1 liter container. So really, I'm just comparing the different pressures. And I know that if pressure is larger, then my moles is larger. So notice my different pressures. B has twice as much pressure as A and C, which means it has twice as many moles as A and C. So when I look at my molar masses, let's say that A has 1 mole and C has 1 mole. B would have 2 moles because it's twice the pressure at the same temperature and same volume. And so therefore, my grams is molar mass times moles. So I would really just have 16 grams of methane, I would have 60 grams of ethane, and I would have 58 grams of butane. So my density, grams per mole, is the greatest in container B because I have the greatest number of grams in the same volume. When a sample of oxygen gas in a closed container of constant volume is heated until its absolute temperature is doubled, which of the following is also doubled? So I'm thinking again of my ideal gas law. So I am, volume is constant and it's heated until absolute temperature. That means the temperature in Kelvin is doubled. So if I double T, so now I have 2T, which of the following would also be doubled? The density of a gas. Well, when we're looking at density, we're looking at grams per liter, constant volume, so our liter is not changing, and all we're doing is we're changing the temperature. So we're also not changing the mass. So that can't be. The pressure of the gas, if I double my temperature and volume stays the same, well then pressure has to double in order to keep this statement true. So it would have to be B. The average velocity of gas molecules, although when temperature increases, the velocity of gas molecules increases as well. It's actually squared, and we'll talk about that relationship a little bit later. The number of molecules per centimeter cubed, I'm not increasing or decreasing my amount of molecules or my volume, and so this can't be true. And the potential energy of the molecules, when we are talking about temperature, we are talking about kinetic energy. So if we say the temperature is doubled, then the kinetic energy is also doubled, not the potential. Okay.